And this is May 2012 Practical Exam 1. So again, we're going to do a little bit of practice on writing the formula of the complexes formed in these different identification tests. And the question asks us to determine the complex formed in 4, 5a and 5b. But also we can have a wee look at the complex formed in test 2. So let's start there in test 2. What have we done here? We have taken our salt, which is a green salt to start with, and we have added water. We've dissolved it in water, and you can see we've formed a green solution. So what have we formed here? Well, we have formed the hexa-aqua complex. And by the end of all the deductions, we can work out that it's nickel that we have present. So our metal cation that's present is nickel 2+. And as we know, when we add water, it always forms the hexa-aqua complex. And so the formula of our water complex, our nickel complex, is nickel, hexa-aqua, so 6 waters. And because water has a neutral charge, so no charge, and nickel has a charge of 2+, the overall charge of our complex is 2+. So that, if you were asked to write the formula of that would be the complex that we have formed. So let's then go down to test number 4. So what we've done is we have taken some of the solution. So it says here, the solution from test 2, so some of our hexa-aqua solution, and add some EDTA solution. So what happens when EDTA comes in? Well, when EDTA comes in, let's just get it in the right line here. What happens is that the EDTA comes in and it replaces the water ligands. So EDTA is a hexadentate ligand, which means that it can bond in 6 positions. And so it forms a very stable complex because it can bind in 6 positions. So we add in our EDTA and it has the effect of replacing the 6 waters. So what we form is our nickel EDTA complex, and we only need 1 EDTA because it can bond in 6 positions, so it fills that up. We'll leave our charge until the end. And what we have taken out is our 6 waters. So our 6 waters are now free in the solution. They have been replaced by the EDTA ligands. So let's think about the overall charge of our complex. Well, our nickel is 2+, as we can see from here, but EDTA has a charge of 4-. And so we need to total that up. 2+ plus 4- gives us a charge of 2-. So the complex that we have formed in test 4 is NiEDTA 2-. Okay, so now looking at 5a, we have added ammonia. And you can see here that it has been added in excess because we've got a blue solution. So initially it would have formed a precipitate, but it has now formed a solution, and so we can see it's in excess. So what we're doing in this case is we are taking our hexa-aqua nickel complex and we're reacting it with ammonia ligands. And what we can see is that actually all 6 waters are replaced by ammonias. In this case it was different with copper, but now with nickel all 6 are replaced. And so what I end up with is my hexaamine complex. So my 6 ammonia ligands have taken the place of the 6 waters, and so now my 6 waters have been chucked out of the complex, and they are now free in solution. So you just need to make sure that the number of ligands on your left hand side is the same as on the right hand side. So I have 4 water ligands here, or 6 water ligands here and 6 on the right hand side as well, because all 6 have been replaced by ammonia ligands. So this is the hexaamine nickel complex. And again, my charge is 2+ because ammonia is also a neutral ligand. Okay, and finally we need to consider the reaction when we add 1,2-diaminoethane to our complex. I've underlined that in pink because we get a characteristic pink colour for nickel and the diaminoethane test, and this is a test for nickel ions specifically. So again, if we were asked to write an equation, so what we've done is taken our hexa-aqua complex, our nickel solution, and we've added in our ethylene diamine, or our 1,2-diaminoethane. They're both names are for the same molecule. And what do we know about 1,2-diaminoethane? Well, let's draw its structure here. 1,2-diaminoethane, well, ethane gives me the clue that I'm going to have 2 carbons. And then 1,2-diamino, that means that on carbon number 1 and carbon number 2 I have an amino group, which is NH2. And then I can fill these up with hydrogens. So 1,2-diaminoethane. And how does this act as a ligand? Well, it might be even simpler if we write this in the simplified form. And that's by using just lines to represent my carbons. So at each point there is a carbon, but here I have my NH2 groups. So you can see now here the shape of 1,2-diaminoethane and how it can kind of bend round, and so that these can then act as ligands. And what they do, how it acts as a ligand is the lone pair on the nitrogens. They coordinate with our metal ion. So if we think of nickel 2+ in the centre here, they can coordinate like this. So judging on the shape of 1,2-diaminoethane, it can fill 6 positions, and nickel has 6 positions in total available. Each 1,2-diaminoethane ligand fills 2 of those positions. And so in total I can fit 3 diaminoethanes around my nickel ion. And so going back to our equation up here, I add 3 1,2-diaminoethane ligands, and we just simplify that using the shorthand version EN, a bit like EDTA, and we don't write the full name of it. And what that does is it replaces the 3 EN ligands, which we can say are bidentate, so they coordinate in 2 positions. Those 3 bidentate ligands replace the 6 monodentate aqua ligands. And so what I end up with is my nice pink nickel EN3 complex. We'll worry about the charge in a second. Plus 6 waters, which are now free in solution because they have been replaced. Those ligands have been replaced by the 3 bidentate diaminoethane ligands. Let's think about the charge. We're going back to, we have the structure of 1,2-diaminoethane below us here. And you can see that there's no overall charge on our on our ligands. And so again, the complex just carries the charge of the ion, which is 2+. So that's how we write the formula of the complex formed in test 5b. Now the last part of the observations test asks us why a reaction happens in test B. So basically, why does this reaction proceed in the forward direction? And the reasoning of this is based on entropy. So what you need to do is determine the number of molecules on the left-hand side of the equation and the number of molecules on the right-hand side. So here we have our 1 complex molecule and our 3 1,2-diaminoethane ligands. And so that's a total of 4 molecules. On the right-hand side, because we've freed up our aqua ligands, our water ligands, we have our complex ion plus 6 waters is 7 molecules. So moving to the right-hand side, we have an increase in the number of molecules, and so an increase in entropy. So you can explain this in a couple of different ways. You can make the point that there's more molecules on the right hand side, or that 3 EN ligands replace 6 water ligands. But then the last point that you need to make, so it can be one of the two of these, and the last point you need to make is that has a result of increasing the disorder or entropy of the system. And chemistry always favours the reaction which produces more disorder. So the reaction proceeds to increase the entropy of the system, and we can see that there's a higher entropy on the right hand side because there are more molecules.